Let's go over one of the past paper questions from paper one, AQA A-level chemistry. One of the common questions in paper one is about the Born-Haber cycle, and this is thermodynamics. So this question is about enthalpy changes. The first question, they ask you to state the meaning of the term perfect ionic model. Perfect ionic model has three different properties you can talk about, and if you talk about one of these would be enough to get you the mark. So you can either state that ions are point charges, or ions are perfect spheres, or there is no covalent character in ionic compound. Any of these will give you the 1 mark. So I can just write one of these, which are ions are point charges. So that should give you the mark. And then they give you the Born-Haber cycle for the formation of a sodium oxide. And there are two missing components in this Born-Haber cycle, and they want you to write the formulas, including the state sample of the appropriate species on each of the two blank lines. Remember, in the Born-Haber cycle, we start off with the formation of the ionic compound, or the standard formation of the ionic compound from their species and their standard form, from their elements and their standard form under standard conditions. So here it's sodium oxide, which is solid. And here in the first blank line, you need to write the standard form of the different elements that formed the sodium oxide. We have two sodium and we have one oxygen. So sodium will be 2 of the sodium, and the sodium, the standard state of the sodium is solid. So it's 2 of the sodium as solid, plus only one oxygen, which means half of the O2, and this is going to be gas. The next two steps will be the atomization. So they started off with the atomization of oxygen, and the second step was the atomization of the sodium. And then the next step will be the ionization. So ionization of sodium first, and this was followed by the electron affinity for the oxygen, first and second electron affinity. So now we need to write the species for the first ionization of the sodium. Again, we have 2 of the sodium. So now we're going to have 2 of the sodium, which are going to change into sodium ion, Na plus, and it's in a gaseous state. Don't forget the 2 electrons that come from the ionization of the 2 sodium atoms. And then finally, the oxygen doesn't change here. So oxygen as a gas. Now we have completed the 2 missing species, or the 2 lines which had missing species. Now the next question is that they give you the enthalpy changes, the different enthalpy changes of the different steps of the Born-Haber cycle, and they ask you to calculate the enthalpy of the lattice dissociation of sodium oxide. So now we need to put the values from the table into the Born-Haber cycle and do our calculation. So the first one, the first step here, this is going to be the formation, a standard enthalpy of formation of sodium oxide, and we can find it here from the table. So this is minus 416. So this is the first one. And then the second one is the enthalpy of atomization of oxygen, and enthalpy of atomization, because this has changed. This is the first one here, atomization of oxygen, and the atomization of oxygen plus 246. So here is plus 248. And then followed by the atomization of the nitrogen. But remember, there are 2 moles, so we have to multiply this by 2, and this is 109 plus 109. So there is 2 times 109, and also this is with a plus sign. And then followed by the ionization of the sodium. And the first ionization energy of sodium is plus 494. Remember, there are 2 of the sodium, and so this is going to be plus 2 times 494. And then we have the first electron affinity for the oxygen, which is minus 142. So this is minus 142. And then this is the second affinity, the electron affinity for the oxygen, which is plus 844. So here plus 844. And then this is the enthalpy of the the enthalpy of the lattice of dissociation, the enthalpy of the lattice dissociation of the sodium oxide. Now, following the following the Hess's law, the arrows that will, or the steps with the same direction of the arrow, the total enthalpy change for these will equal the total enthalpy change for the ones over the opposite direction. So now these two will have the same direction. So this is the enthalpy of formation and the enthalpy of the lattice dissociation. This is the total of these will equal the total of the other steps, which are the ones with the crosses. So 1, 2, 3, 4, and then here the fifth one. Now we just need to add our values and then do our calculation. So now that means that the enthalpy of lattice, the enthalpy of lattice dissociation plus the enthalpy of the formation, which is plus minus 416, will equal the total of the other ones, which are the 248 plus 2 times 109 plus 2 times 494 plus minus 142 plus 844. When you do this calculation and you move the minus 418 to the other side with the opposite charge, then the final answer will give you plus 2572 kilojoule per mole. So this is the enthalpy of lattice dissociation of the sodium oxide. The next question, they ask you to explain why the second electron affinity of oxygen has a positive value. Remember that for the second electron affinity, you have a negatively charged ion which gains electron. So there will be repulsion between the negatively charged ion and the electron that is gained. So this is why it will have a positive value. So this is because oxygen ions will repel the electron gained, or the electron being added, or will gain will repel the electron. So you can just say the electron being added. And that will give you the 1 mark needed for this particular question.